So hello everyone, welcome to the new video, and in this particular video we are actually going to understand that what exactly is the meaning of zero temperature drift. Okay, so if you could remember, in the previous session we had seen this particular thing. We will quickly revise what all things we had seen in the previous session. So in the previous session what we saw is that as the temperature, or rather as the surrounding temperature of the JFET increases, two phenomena takes place at the same time, that is increase in ID and decrease in ID. Okay, so what we saw is that during normal condition there isn't any significant change that happens in the drain current, that is ID, right? But as the temperature increases, the drain current decreases. Why? Due to due to the vibration of the lattice atoms, which is present over here, you can clearly see, and due to which the velocity of the electrons decreases, and thus eventually the current ID also decreases, right? But at the same time the another phenomena happens, that is increase in drain current ID, and this is because we all had already seen this particular part, that is the electrons, okay, which are present in the depletion layer, or rather which takes part in the formation of depletion layer. It decreases and it it ejects out of that particular depletion layer, and it takes part in the conduction, right? Due to which the current ID also increases. Okay, so these two phenomena takes place at the same time, right? So this is what we saw, and at the end we also saw this, that is the decrease in current ID, it is 0.7% per degree Celsius. So I just made a mistake over here. It is 0.7% per degree Celsius. That means what? As the temperature increases by 1 degree, so the current ID decreases by 0.7%. That means what? If let's suppose at room temperature, if the current ID it is 1 milli, right? It is 1 milliampere, and let's suppose if I increase the surrounding temperature to 26 degrees Celsius, so that means what? You are increasing the temperature by 1 degree, so the ID decreases by 0.7%. That means 0.7% of 1 milliampere. So that would be the decrement in the ID, right? And the increase in ID, it is around 2.2 millivolts per degree Celsius into GM, right? So this is what we saw in the previous session, if you could remember, right? Alright, so now what we are going to do, we are going to see what exactly is the meaning of zero temperature drift. Okay, so we had seen half of the part, or rather we had seen the very first part. We had tried to understand what exactly the situation might happen in case of JFET internally, but still why exactly this particular concept, it is known as zero temperature drift. We are unaware of this particular concept. Okay, so we are going to understand this particular word in today's session, or rather in this particular session. Okay, so let me proceed further, and let me just take two lines, or rather two arrows. So this is the first arrow and this is the second arrow. I will tell you the reason why I am taking this particular thing into account. Alright, so let me write over here, that is ID, current ID is decreasing. Okay, ID is decreasing, and its value is around 0.7%. It decreases by 0.7% per degree Celsius, okay, into ID, right? And we also saw that at the same instant what we saw is this, that is ID increases, so ID increasing, okay, ID increasing at around 2.2 millivolt per degree Celsius into GM, right? So we saw this particular two things. So are you able to understand this particular part? See, at the same time ID is decreasing, and at the same time ID is increasing, right? So basically, let me write over here, we will get one point, just a second, we will get one point. Let's assume this is point A. So let's assume this is point A. So basically we will get this particular point A where the ID won't show any change with respect to temperature. I hope you are getting this particular point. See, that means what? These two particular equation, or rather these two particular currents ID, they will try to cancel each other at one particular point. That means you won't be able to see any significant change in ID, or rather you won't or rather you will see zero change in ID, zero change in ID with respect to temperature. So let me write over here. See, that's why I had taken this two particular arrow indicating that they are cancelling each other. So what I want to say is that is at point A, let me shift this particular whole of the diagram over here. I know this may sound little confusing as of now, but make sure once we deduce certain things out of these particular equations, you would be in that particular scenario to understand this particular concept in depth. Okay, so at point A, what we see is that no change in ID, no change in ID, just a second, no change in ID with respect to temperature, with respect to temperature. Okay, again I am repeating this particular part. See these two equation, I mean the current ID is decreasing with respect to temperature, and at the same time the current ID is also increasing with respect to temperature, right? So basically we will get one point wherein the ID won't show any significant change with respect to temperature. Okay, so this is what I wanted to convey, right? So see, what I want to convey is that basically now just with the help of this particular diagram we understood that we are not getting any significant change in ID with respect to temperature, right? So what I want to say is that, so can I write this particular equation in this way to get that particular point? Obviously that is a decrease in ID, I'll write it in this way, decrease in ID is compensated with increase in current ID, increase in current ID. Okay, so that means what? Can I write it in this way? Obviously I can obviously write this particular whole of the thing in this way. That is, what is decrease? Decrease is around 0.7% per degree Celsius of ID. Okay, so this is what this is the decrement in ID with respect to temperature, and at the same time you can clearly see that there is an increase in ID, that is equivalent to 2.2 millivolts per degree Celsius into GM, right? So these are the two equations that we had seen. So basically these two equations, they are carried out experimentally. Okay, so someone has performed that particular experiment and then they might have got this particular equation. Okay, so don't worry about this particular equation, how we exactly got this particular equation and all. We just need to find out that particular point where where there isn't any change in ID with respect to temperature, or the change in ID would be negligible, right? So you can clearly see from this particular equation that I can cancel out this, that is degree Celsius and degree Celsius. Okay, and if you could remember, we had already seen the formula for ID and we had already seen the formula of GM, right? That's why I told you that we are studying certain parameters to understand certain things. So that's why I took transconductance, that particular if you could remember that particular session, the parameters, right? Then we also saw the amplification factor, and also now we are going to use this particular parameter over here. Okay, so let me write over here, this is 0.7%, or rather I will write it in this way, that is 0.007, right? Because any which was percent you can divide by 100, right? Into what is ID? If you could remember the formula for ID, it is ID, it is equivalent to IDSS. Let me write over here, IDSS into 1 minus of VGS by VP the whole square, VGS by VP the whole square. If you could remember this particular formula, okay, I hope you remember this particular thing and this particular formula, and it is equivalent to 2.2 millivolts. 2.2, can I write millivolts in this way? That is 10 raised to minus 3, right? Of course I can write this particular equation in this way, into what is GM? And if you could remember the formula of GM, it is minus 2 IDSS minus 2 IDSS by VP into bracket, I will write this bracket in this way, that is into 1 minus of VGS by VP, VGS by VP. So you can clearly see when I equate this to equation, so what I will get is this, that is I can easily deduct this square and I can easily deduct this particular 1 minus of VGS by VP, right? So what we are left with is this, that is 0.007 into IDSS into 1 minus of VGS by VP, right? Into IDSS into 1 minus of VGS by VP, right? And this is equivalent to just a second, yeah, this is equivalent to 2.2 into 10 raised to minus 3, so it is equivalent to just a second, yeah, 2.2 into 10 raised to minus 3 into minus 2 IDSS by VP into minus 2 IDSS by VP, right? And you can clearly see from this particular equation we can easily deduct this two particular term, that is we can easily cancel out this two particular term, that is IDSS, and what we are left with is this. So I can easily multiply this, and what I will get is this, that is 4.4, just a second, yeah, 4.4 into 10 raised to minus 3, right, into 10 raised to minus 3 divided by VP. Obviously it is in volts. Okay, we had just taken the 10 raised to minus 3. This is volt, you can clearly see it is volt. Okay, so let me write over here, this is volts only, this is volts. Okay, that is the unit, right? That is the unit of this particular thing, that is this particular you can clearly see over here this particular number, it was 2.2 millivolts, right? Since this was our VGS, right? If you could remember, we had already seen in the previous session, and we had just taken this millivolts, that is 10 raised to minus 3, but this volt will remain as it is, that is its unit, right? And this is, now I will also multiply this particular thing, just a second, I just forgot to write my minus sign over here. So over here there should be one minus sign, that is minus of 4.4 into 10 raised to minus 3 divided by VP, right? Great. And over here this would be 0.007 minus 0.007 VGS by VP, right? And now what I will do, I will just multiply this particular equation with VP. So this particular equation would be 0.007 into VP minus of 0.007 of VGS. Okay, and this is equivalent to minus of 4.4, just a second, yeah, minus of 4.4 into 10 raised to minus 3 volts. Okay, into 10 raised to minus 3 volts. Okay, all right, great. And now if you could look very clearly, like this whole of the term, it is in volts, that is VP, it is voltage, right? VGS is also voltage, and over here this is unit V, right? So you can easily cancel out this particular units. Obviously we all know the unit of voltage is V, right? So we can easily cancel out this particular V. Okay, so that's why I had, like, that's why I'm not writing this particular V. Okay, all right, great. So what you can do, you can take 0.007 as common from this particular term. So this would be VP minus of VGS, and obviously I will write this in bracket, and this would be getting multiplied with 0.007, and this would be equated with minus of, just a second, minus of 4.4 into, just a second, 4.4 into 10 raised to minus 3. Again I'm repeating why I cancel this particular unit of V, unit of voltage. See, this was VP, which is a voltage, right? Unit of this would be V, unit of this would also be V, that is VGS. Again this is a voltage, and over here there was one V. Okay, unit of, that is unit of voltage. Okay, so if you could see, its unit is V, its unit is also V, right? So if I take V as common from this particular two terms, so obviously V will be getting common, and this particular V would be would get cancelled out with this particular V. Okay, so that's why I just cancel out this particular V over here, which was present over here. Okay, all right. So what I will do, I'll just copy this particular equation, or rather I will, just a second, write in the next page only. So let me write this particular equation over here, that is VP minus of VGS, just a second, VP minus of VGS, and this was in bracket obviously, and this is equivalent to minus of 4.4 into 10 raised to minus of 3, right, into 10 raised to minus of 3, and then it is divided by 0.007, right? So let me just calculate this particular term, and this pans out to be minus of 0.628. Okay, so VP minus of VGS, it pans out to be minus of 0.628. 0.628, and I can write this minus of 0.628 as minus of 0.628 can also be written as 0.63, right? It can also be written as 0.63. So at the end we get the value of, we get one equation that is just a second, that is Vp minus of VGS, Vp minus of VGS, it is equivalent to minus of 0.63. I just did a small mistake over here, 0.63. So over here there should be one negative sign. Just a second, let me show it over here. So there should be one negative sign. Okay, alright, so I hope you understood this particular part. Let me just highlight this particular equation. Still there is one concept remaining to decide, to discuss, that is zero drift temperature, or zero drift biasing. That that I will discuss now only, don't worry. But there is one more thing to write over here. So VGS, can I write this particular equation in this way? That is VGS, it is equivalent to VGS, it is equivalent to VP plus 0.63, VP plus 0.63, VP plus 0.63. So I will again highlight this particular equation. So what does that means? So basically we had obtained this particular point, if you could remember the transfer characteristic. Okay, so if we equate VGS equivalent to VP plus 0.63, so at this particular voltage we would be getting the current which won't be having a significant change with respect to temperature. So basically at this particular point, so in transfer characteristic, at VGS equal to VP plus 0.63, at VGS equal to VP plus 0.63, or at this particular point, the current ID won't show any significant change, or current ID won't show any significant change, or the change would be almost negligible. If you can't change with respect to temperature. What does that means? That means, see, even if our temperature or the surrounding temperature of the JFET is increasing, okay, obviously from 25 degrees Celsius, if it is getting increased to around 30-40 degrees Celsius, then it can bear. Okay, otherwise you will think that from 25 degrees Celsius I'm directly jumping to 100 or 150 degrees Celsius. No, it's not like that. Okay, in that particular situation even our skin can burn, right? So the JFET cannot sustain at that particular temperature. But yes, if the temperature, that means if the surrounding temperature of JFET it is around 30 to 40 degrees Celsius, okay, from 25 degrees Celsius it got increased to around 30 to 40 degrees Celsius. Okay, and if we are biasing JFET at this particular point, so it won't show any effect with respect to temperature, or rather it will show zero effect with respect to temperature, and that's why it is known as zero temperature drift. Okay, that means what? At this particular point the current ID won't show any significant change with respect to temperature. So that's why this particular whole of the concept, it is known as zero temperature drift. Okay, that means at this particular point JFET will show zero drift with respect to temperature. The current of the JFET will show zero drift with respect to temperature. And what is that particular point? So this is that particular point. So let me just show you one graph. So this is T1, T2, T3. So you can clearly see this is T1. Let's assume it is 25 degrees Celsius. So T1, it is, let me take a different color, maybe this one. Yeah, so T1 is around 25 degrees Celsius, T2 is around maybe 30 degrees Celsius, and T3 is around maybe 35 degrees Celsius. So you can clearly see from this particular graph that at around at less temperature the current ID is quite maximum, right? So ID max, ID1. Okay, and as the temperature is increasing from 25, it got increased to around 30, so this would be ID2, right? And over here this is ID3, right? When as I increase the temperature, I got value of current as ID3, and you can clearly see the curve for ID1, ID2 and ID3. So you can clearly see, if I plot this particular curve, I got one particular point where the current won't show any significant change with respect to temperature. So let me write over here, my ID1, it is greater than ID2, it is greater than ID3. What does that indicate? It indicates that for temperature T1, which is less than, obviously, which is least temperature, the value of current would be high, and as I'm increasing the temperature, so the value of the current is decreasing, right? But if you plot this particular curve, you will get one point where the current shows zero effect with respect to temperature. That means for that particular point, all the curves will pass through it. I hope you're getting this particular point, and this particular point is nothing but VP plus 0.63. So let me write over here this particular point, it is this particular point, or VGS, it is VGS is equivalent to VP plus 0.63. So if you could remember, in case of JFET, since we are dealing with BFW10, so for BFW10, let me write over here, for BFW10, we all know its VP is around it is around minus 8 volts, right? Minus of 8 volts. Okay, so to make this particular, to make the current of JFET, or rather to make the current of BFW10, independent of temperature, right? That means our ID, or the current ID, it is not dependent on the temperature, right? So to achieve this particular condition, we have to set, or rather we have to take VGS. So VGS should be equivalent to VP plus 0.63 volts. That means we have to bias this JFET at around minus 8 plus 0.63. okay, so we have to bias this particular JFET at around, let me just calculate this particular value. So it is minus of 8 plus 0.63, so this is minus of 7.37. so basically we need to bias this JFET at around minus of 7.37 volts, okay, roughly around this particular value, to make sure that the JFET, the current flowing through the JFET, it is independent of temperature. Okay, so let me write over here, so when VGS, it is equivalent to minus of 7.37 volts, so the current flowing through the JFET, the current flowing through the JFET, which is ID, right? It is ID, it will be independent of temperature, it will be independent of temperature. Okay, so even if the temperature is increasing, still the current flowing through the JFET, it will be as it is if we are maintaining that particular JFET at this particular point. Okay, if we are biasing that particular JFET at this particular point. Okay, and again I'm repeating why it is known as zero temperature drift. Again, what all things we discuss. See, first of all, I discussed this particular point. See, your ID is decreasing, right? And at the same time ID is increasing. So basically we will achieve one point where that particular ID will remain constant, okay, irrespective of the temperature. Even if the temperature is increasing, still the ID will be maintained at that particular same point. So for that, I equated this to equation, that is decrease in ID is getting compensated. Decrease in ID, it is getting compensated with increasing ID, right? So when I actually equated this to equation, I got this equation, that is just a second, yeah, that is minus of 0.63, right? So if I try to solve this particular equation further, I got this equation, that is VGS, it is equivalent to VP plus 0.63. okay, and so in transfer characteristic, at VGS equivalent to this value, the current ID won't show any significant change with respect to temperature, and this particular condition, it is known as zero temperature drift condition. That means the change in current would be zero with respect to temperature, that's why it is known as zero temperature drift. Okay, And now I hope that you understood this particular concept in depth. That means what, if we are maintaining this particular, if we are biasing this particular JFET at this particular point where VGS is equivalent to VP plus 0.63, so whatever the current that we would get, it would be in stable condition, okay, respective of the temperature. Okay, so this was for BFW10. If you want, I can also derive for BFW11. So let me write over here for BFW11, and generally, in most of the universities, they take this particular JFET, that is BFW11. We all know what is the VP of it. So its VP is, since we had seen the data sheet, or if you don't know how to refer data sheet, or rather how to take the values from the data sheet, you can watch my previous video. It is already uploaded there. Okay, it is minus 6 volts, right? So to make sure that the current flowing through the JFET, it is independent of temperature, so we need to set this VGS in such a way that it should be equivalent to VP plus what, 0.63. so if you could see very clearly, this equation would be minus of 6 volts plus 0.63 volts, obviously, so 0.63. so let me just calculate this value very quickly. Minus of 6 plus 0.63, this pans out to be minus of 5.37. So what we exactly what we need to do is that we need to keep this particular VGS equivalent to this voltage to assure that there would be negligible effect of temperature on that particular current ID flowing through this particular JFET, 5.37 volts. Okay, so let me just highlight these two equations, or rather these two things. This was it. Yeah, VGS is equivalent to minus 7.37 volts. Okay, so I really hope that you understood whatever concepts that we had discussed in depth. Okay, whatever the concepts that we had discussed till now. But still, if you are facing any difficulties, if you have any doubts anywhere, you make sure to ask me in the comment section. I will surely help you out there. Okay, so thank you for listening me patiently. I am ending this video over here. Thank you.